Guys, welcome back. Today we're going to be discussing theoretical probability and experimental probability. So let's talk about theoretical probability first. So you can kind of hear the word theory in the word theoretical. So theories are basically ideas or concepts that really take place, but there aren't really much proof to hold on to it. So that's what theoretical probability is. So I have a definition up top. So it's what should happen during an experiment. So we'll discuss that in a couple examples below. And then our experimental probability. So that is when you actually do the experiment. You're actually flipping the coin or rolling the number cube or whatever it is. So that's what actually happens during the experiment. Are they always going to be the same? No. Could they? Yes. So let's jump right into examples. Let's start right here. So we need to find the theoretical probability of rolling a number cube and getting a 2. A number cube is just like your normal dice that you get in a game of Monopoly. So you have numbers 1, 2, 3, 4, 5, and 6. So you want to know your theoretical chances of getting this number 2. Well, there's only one 2 in this whole data set right there. So only one option for me, and there are 6 options. That's going to be my denominator. Your denominator is something called your sample space. That's how many possible outcomes you have. So that is your theoretical probability, nothing else you can do. Let's find the theoretical probability of spinning a spinner and getting the blue. So I'm going to draw my spinner real quick. So this one will be blue, and these are other colors. They are not important, but they are not blue. So there are 4 total options that we could pick from because the spinner is divided into 4 pieces, and there's only one outcome I want, which is blue. So my theoretical probability for this example is just 1 over 4. And the last one here. Find the theoretical probability of flipping a coin and getting a heads. Well, there's only one heads on every coin that I know of, and there's 2 options. So your fraction is just 1 over 2. As you can see, there is a bit of a trend going on. Most theoretical probabilities will have that numerator of 1, and all theoretical probabilities will have that denominator of your sample space, how many possible outcomes you have. So let's see how it can be different than our experimental probability. So we're going to be calling this example up here, we'll call this example 1, and we'll call this one down here 1b, because it kind of relates to each other. So you can't find experimental probability unless they give you experimental data. So in this case, we rolled this number cube 30 times and we got the number 12, we got the number 2 12 times. We want to know what the experimental probability is. Well, we did this experiment 30 times. That's going to be our denominator. And we got a 2, they told us 12 times. That's our numerator. And I can reduce this fraction. I can divide this fraction by 6. So I will divide the top and bottom both by 6. And I get 2 on top and I get 5 on bottom. So as you can see, the probabilities from 1 and 1b are completely different because the experiment, you never know what's really going to happen when you do this experiment. If you wanted your experimental data and your theoretical to be really similar or even the same, the more times you do an experiment, the closer and closer it will get. And we have this one over here that deals with the coins. We're going to call this one 3, and we'll call this problem 3b down here. So if you flipped a coin 100 times and you got heads 30 times, what is your experimental probability? Well, I got 30 when I ran this, and I did the experiment 100 times. So my fraction is 30 over 100, but I can simplify that and divide each of them by 10. So my fraction, simplified, will be 3 over